One of the defining features of modern science is that scientists have to communicate their findings. In fact, this is what makes science work. It's only by putting your ideas out there that other scientists can review them and critique and improve on them. But we don't just need to tell other scientists what we found. We also need to tell non-scientists. After all, one of the goals of science is to improve life for society as a whole. This is quite nicely summed up in this quote from scientist Anne Rowe. Nothing in science has any value to society if it is not communicated and scientists are beginning to learn their social obligations. Now, that was written 70 years ago, and while there is a lot of effort in modern times to popularize science, I would argue that this is an important skill that each generation of scientists needs to learn. Much of modern science revolves around collecting and analyzing data. Unfortunately, raw data is often hard to understand. Here's a table showing the number of pedestrian deaths in the USA each year. These are people who died in some kind of traffic incident. It's a bit hard to spot any meaningful trends when we just have a table of raw numbers like this. Sure, we could go through row by row and try to remember all the numbers of previous rows, but the human brain just isn't really designed to work that way. But what the brain is good at is looking at images and pictures. There's a famous saying from the newspaper business that a picture tells 1,000 words. Or to put another way, you can write a long article about some story, but a powerful image can often communicate the story just as effectively. As scientists, we can hook into that strength of the human brain by converting our data into pictures. A picture of a data is called a graph, and we are going to spend some time learning not only how to create graphs, but also how to pick the best type of graph to communicate what you want to show. For example, we can convert our table of US pedestrian deaths per year into a graph, and suddenly that data becomes meaningful. We can see that deaths were declining through the 90s and the noughties, and then around 2009 to 2010, the trend changed. The number of pedestrians dying on America's streets has been growing ever since. Let's consider another example where better communication of data might have averted a disaster. That disaster was the explosion of the Space Shuttle Challenger in 1985. Afterwards, there was a big congressional investigation into why this had happened, and one of the findings was that the failure had probably originated with a particular rubber seal in part of the rocket. It was very cold on the day of the launch, and as you may know, rubber can become very brittle when it gets cold. But the investigation also found that the NASA ground crew knew that this was an issue with this particular seal. The company that engineered those rubber seals had expressed its concern about this failure to NASA and pointed out in previous shuttle launches the seals had become progressively more damaged on colder launch days. But ultimately NASA decided to go ahead. I don't want to second guess their decision. After all, launching yourself into space on what is essentially a bomb full of rocket fuel is always going to be risky, and part of their job is to decide when the risks are acceptable. But we can look at how the data about the seals was presented and whether that method of communication clearly illustrated the problem. It turns out the data was presented in tables like this. This doesn't include the temperature information, which was presented in a different location, along with some additional bullet point notes recommending that the launch not go ahead if the temperature was lower than 53 degrees Fahrenheit. Even to people working on the shuttle every day who would have been intimately familiar with its engineering, it's hard to see the magnitude of the problem here. After the disaster and the inquiry, an expert in data visualization called Edward Tufte suggested that the problem would have been much clearer if it had been presented in a graph like this one. Now we can see that the damage is clearly increasing at lower temperatures. We've got temperature here on the x-axis, low temperatures on the left, high temperatures on the right, and the amount of damage to the seal is on the y-axis. We can see that as the temperature goes down with the data that we have from previous launches, the amount of damage starts to increase quite significantly. This shaded red region is the temperatures that were forecast on the morning of the Challenger disaster, which are not only a lot lower than the temperatures of previous launches, but if this trend were to continue, it sort of implies that the seal would have undertaken a lot of damage.